Hello everyone, I am Rodolfo Bojorque, and I will present a study conducted with first-year engineering students in Ecuador, where we explore a simple but powerful questions. Can we significantly improve mathematical problem-solving skills by restructuring how we use classroom time? Our focus was not on technology, not on curriculum design, but on something much more practical: continuous supervised practice. Objectives. I will briefly. First, describe the educational problem we faced. Second, explain the instructional intervention. Third, present the quantitative results. And finally, discuss what this means for engineering education more broadly. In many universities, first year's mathematics courses show high failure rates. Students often report low engagement, difficulty applying procedures, anxiety towards abstract concepts. The traditional lecture models dominate. Professor explained, students listen. But mathematics is not learned by watching. It's learned by doing. This mismatch motivates our study. Engineering education requires more than memorization. Students must apply procedures correctly, analyze unfamiliar problems, transfer knowledge to real contexts. If students cannot develop higher order skills early, this affects their entire academic trajectory. So, our research question was very direct. If we implement continuous supervised practice inside the classroom, will students improve in application skills, complex problem solving, and with conceptual understanding remain stable? Context. The study was conducted in linear algebra course. More than 400 first-year engineering students. 2 consecutive cohorts, one traditional lecture-based, one with the new intervention. Students shared same syllabus, same exams, same evaluation criteria. The key difference was how we use class time. In the traditional model, most time was spent explaining theory. Practice happened later. The students are alone. In the new model, short explanations. Most of the session dedicated to supervised problem solving. Immediate instructor feedback. The structure change, not the content. The class structure. Each session follows a simple cycle. Short conceptual explanation, extend guided practice, feedback, and clarification. This ensured continuous engagement, distributed practice, immediate correction of misconceptions. The study design. We use a quasi-experimental cohort comparison design. We compared baseline cohort versus intervention cohort. This was not randomized, but both groups were academically comparable and evaluated with identical assessments. We evaluate performance across three dimensions. First one, understand, conceptual knowledge. Second, apply, procedural execution. And third, solve, complex non-routine problems. This represents increased cognitive demand. Our hypothesis was that supervised practice would especially impact applied and solve. Here are the main differences. Understand increases slightly. Apply improved by 5 points. Solve improved by 8 points. Considering the exam was graded over 35 points, these are meaningful gains, especially in higher order skills. This comparison shows a clear pattern. Conceptual understanding remained stable. Application and problem solving improved substantially. The intervention did not sacrifice theory, it strengthened practice. The statistical analysis confirms this. The improvement in apply was significant. Solve was highly significant. Understand showed no significant change, but importantly, it did not decrease. Beyond numbers, instructors observed higher engagement, more participation, greater confidence during exams. Students were less hesitant to attempt complex problems. This behavioral shift supports the quantitative findings. The core contribution is simple. This is low cost, scalable, technology independent. It can be implemented in large classrooms without additional infrastructure. Why does it work? Because learning mathematics requires distributed practice, immediate feedback, active cognitive processing. The classroom becomes a practice environment, not just a lecture space. Educational implications. This approach is particularly relevant for large STEM courses, institutions with limited technological resources, programs seeking to strengthen problem solving without curriculum redesign. It is transferable and realistic. Let me conclude with one idea. Lecture transmits knowledge, practice builds competence. If we want engineers who can solve complex problems, we must allow them to practice consistently and with supervision. Thank you very much.